All right, hello. This is the video for notes set 13, properties of intermolecular forces. So the question here, the big question that we're trying to address is how do intermolecular interactions, this is just another way of saying IMFs, right, intermolecular forces, how do IMFs help to establish macroscopic properties? These are what this is meaning. Is observable phenomenon. So we can't actually see the intermolecular forces, right? We can't see atoms, we can't see molecules, so we can't see the interactions that's going on between the different molecules. But we can see things like in the previous video, I showed you the video, the spider walking on the toilet water. And that property is called surface tension, and it's caused by intermolecular forces. We can also look at properties like something's state of matter, whether it's a solid, a liquid, or a gas. Some other ones that usually fall into this macroscopic properties are the melting point and the boiling point. Since the state of matter is important, the transitions between the states of matter are also important. So, just as a review, states of matter, whether a substance is a gas, liquid, or solid, depends on the battle between the intermolecular forces, which try to sticky different molecules together. Every substance has its own amount of IMF. It doesn't change, it's just sticking them together. And the opposing force is the energy. Specifically, this says kinetic energy, which is energy of movement. And the energy going in is trying to get them to move apart. So this is to sticky the molecules together, and this one is trying to create movement apart to disperse them. So it's a battle between these two. The intermolecular forces are staying the same, but we can change the energy. And by changing the energy, we can kind of see like, when do the IMFs stop holding? Like if something is a solid and it's a solid and you keep adding more and more and more energy, we can say, okay, what point is it not a solid anymore? And that tells us something about how strong it was being stuck together, right? That's where state, melting, and boiling point come into play. So the intermolecular forces based on Coulomb's law, Coulomb is just another word for charge, the idea that opposite charges attract and the same charge repels. So intermolecular forces from the other day, we were saying come from partial positive ends of one molecule. They have partial positive, partial negative. And in a separate molecule, when there's an attraction based on those charges, that's the IMF. So this is just saying based on Coulomb's law, based on that this is negative, this is positive. We're also going to look at the distance between them. And those are the properties regarding the IMFs. Kinetic energy we're going to be looking at what's the temperature, how much energy went into it, how fast are the particles moving, because speed and movement is what kinetic is all about. So here's really the crux of the issue. These two are constantly battling, and we're trying to see, can the IMFs hold it together, or is the energy too great? In the gas state, the kinetic energy is way, way overpowering the IMFs. It's not that the IMFs aren't there, because students will write that on their paper and they'll get it wrong every single year. They'll say, oh, this is a gas, and in a gas there are no IMFs. Look, there's nothing holding them together. Wrong. There are IMFs. There's always IMFs, the same amount of IMFs. But in a gas, the IMFs are very overpowered by the kinetic energy. So it seems like the IMFs are weak. Nothing's changed though, we just have a lot of energy. In the gas state, the particles are far apart, and because of that, they have little interaction with each other. Because they're far apart, they are compressible. You can smoosh a gas into, like think of a pressurized hairspray can or spray paint. You can pressurize it, compress it, because there's a lot of space between the molecules, and you could push them together. You could press them. The opposite example here would be the solid state. The solid state is where the IMFs are super overwhelming. They're way more than the energy that's there. So the molecules are super stuck together, usually in this sort of a gridlock pattern, right? And they can't move. All they can do, they can jiggle and wiggle and vibrate, but they can't actually move from their spot. The energy, the movement is so low. The intermolecular forces dominate so much that the particles remain in position. Solid molecules can only jiggle / vibrate. There is basically no space between the molecules, so solids do not compress. We can't smoosh it any further. Now the liquid state obviously is in the middle between both of those, but in the gas state, kinetic energy is winning. In the solid state, IMFs are winning. We can't just not have a winner. It can't be a tie. And it turns out that IMFs are still winning, but only by a little bit, by like just barely. And we know that the IMFs are still barely winning because the particles are still in contact with one another. Every liquid is still touching another one. It's sticking them together really good. The IMFs stick them together, but the kinetic energy allows them to tumble randomly over and around each other. So that's the difference. In both a liquid and a solid, they're touching with no real space to compress either one of them. But in a liquid, there's just enough energy that these can tumble over each other, whereas the solid is locked in place. Liquids don't really compress much. Its compressibility is considered to be none, like a solid. Subsequently, solids and liquid forms of substances will generally have similar volumes and take up the same amount of space, since in both cases, the particles are in contact at all times. If you look at the next, we'll drop my marker. If you look at the next couple pages of notes, each state gets its own set of notes. I think that notes 14 is the solid state. Double check before you write this down. I think notes 15 is the gas state. Let me look. Yep, okay, so notes 14 and 15, and then maybe there's one more, but this will give you a rough idea of like, this is the basics, and we're going to expand each of these out in a separate section of notes. But for today, we're just doing the grand overview. So the next part is talking about a phase diagram. And a phase diagram looks something like these two pictures here. Or in the homework on the back of homework 13, here's another phase diagram. It kind of splits into 3 spots and has this Y shape. Okay, so the way that these work is on the one axis, we're looking at the pressure, and the other is the temperature of the substance. Okay, sorry, I have to pause the video sometimes. So we've got this Y-shaped thing, and in this region, this is where solids exist. Liquids in this area, and gases. Now, we don't know what substance this is. It says it's a phase diagram of an unknown substance. This could be, I don't know, pretty much anything. And if we knew what it was, cool, we'd be able to say like this substance, when it's at, oh, let's see, when it's at 2 atmospheres of pressure and 150 degrees Celsius. Okay, so that's this line. I kind of tried to draw it in for you. You see that one? So at 2 atmospheres and 150 degrees Celsius, this would be in the solid phase. If we dropped the pressure a little bit to 1.5 atmospheres, so down to 1.5, and cranked it up to 800 degrees, kind of like here, just barely, this would be a gas. Kind of like how water sometimes is a solid, liquid, and a gas, whatever this substance is, depending on the pressure and temperature conditions, it could be a solid, a liquid, and a gas. The point here in the center where the solid gas line, the liquid gas line, and the solid liquid line, where they all kind of converge there, that's the triple point. So the pressure at the triple point, I should have maybe been a little bit better at drawing my picture here. But I would say the pressure where that is at is maybe about 0.6. I don't know. I shouldn't have made the dot so big. I can't really tell. About 0.65 atmospheres of pressure. The temperature of that triple point looks to me about maybe 90. degrees Celsius. It's not to say that at that point you've got solid, liquid, and gas, and it's like a combination of the three. It's just if I took 100 photos, and took 100 photos, sometimes it would be solid, sometimes it would be liquid, sometimes it would be gas. It's like, it's one of them, it could be any of them, but it's not necessarily all of them at the same time. Similarly, if I were to pick a point on this line here, like this point, it's not to say that that's a solid, liquid, whatever. It's just that if I took 100 pictures of that at this substance at 1.50 pressure and whatever this was, 150. If I took a bunch of pictures of that, sometimes it would be in the solid phase and sometimes it'd be in the liquid phase. Okay, if the pressure at 1.25 atmospheres, okay, and 300 degrees, so here, was changed to 0.25 atmospheres. Okay, so we're still keeping it at 300. We're just dropping it from 1.25 down to 0.25. What phase change would be occurring? So I would be in the liquid state to start and then going to the gas state. So liquid to gas we call evaporation. If I went the other way, that would be gas to liquid would be condensating. Liquid to solid, solid to liquid, you know, those ones are melting. So the next one, if I was at, let me get a new marker. If I was at 1.25 atmospheres of pressure and 0 degrees Celsius, which is right here. And then I change it. I'm still going to stay at 0. I'm changing it from 1.25 to 0.25. The question is what's happening here? I'm now going from a solid to a gas. This is called sublimation. When we go from a solid straight to a gas without even going to a liquid first. Just for fun fact, if you went the opposite way, it's called deposition. But it's not what this one's asking. And the last questions, I didn't quite mean to do all the homework, but the last questions here are asking, what are the normal freezing point, normal boiling point, normal melting point? And what it means by the word normal is it means 1 atmosphere, because the pressure that we're operating under determines a lot of stuff. If you've ever made a cake and it says cooking at high altitudes, do blah, 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 and has special directions, those are different than if you're cooking at sea level. Sea level boiling water takes a different amount of time than boiling water on a mountain. So, normal is just the word that we're going to use for 1 atmosphere of pressure, which is sea level. So if we're looking for the normal, let's say normal melting point, we're going to be looking at 1 atmosphere. When do we go? Okay, so melting is from solid to liquid. Solid to liquid crossing at 1 atmosphere. Okay, 1 atmosphere. Oh, right there. Solid to liquid. What's the associated temperature? 100. What about the normal boiling point? Boiling would be from liquid to a gas. So I'm going to follow 1 atmosphere. Boop, 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 boop. There. And where is that? That looks about, I don't know, maybe I drew that kind of weird. I don't know, it looks like maybe 360-ish. I'll put a squiggle. About 360-ish. What is the normal freezing point? So this is from, this is from a liquid to a solid. Now wait, is this going to be any different than our answer from solid to liquid? The answer is no, because it's just depending on if we're going one way versus the other. It's still going to correspond to that same temperature that we used here. So there's you some free homework answers. I didn't quite mean to do that. But this is what a phase diagram is. And for most substances, it looks like this. We've got the liquid in this region. We've got the gas state here. And I've used the same colors up here, not that it matters, but this solid state here. Okay. This is for, specifically, this one is CO2, carbon dioxide, but most substances will look similar in that you have a Y shape, whoop, whoop, and this line going forward. It happened here, it happens in the homework, that solid liquid line runs forward. In water specifically, we have this weird thing happen where that line runs backwards. See, it's leaning left instead of to the right. So just keep that in mind. Water is the exception. And most substances don't do that. Why do you think that is? So the reason that water does this weird thing, most substances, let me go back up to the top here. Most substances have solids and they're really, really, really packed. And liquids are still really, really packed. And then gases are like not packed at all. But with water, this weird thing happens where we're like gas, okay, far apart, that's cool, yep. Liquid, a little bit more squishy, that's cool. And we're expecting solid to be like packed, 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 packed. But it's not. This is the weird one. Water, when it's solid, AKA ice, spreads out. So because this is backwards, the solid liquid transition, that messes up this solid liquid line to lean the reverse direction. So that's why water is a weirdo. Most substances have this forward facing one. Excuse me. Now up here, this is kind of what we were already talking about, the triple point. Here, the normal melting, normal boiling points are where we cross at, like for water, here's 1 atmosphere. There's the normal melting. There's the normal freezing, and you just follow those lines down and see, oh, water melts and freezes at 0 and boils and condensates at 100. And then the critical point, we don't really worry about this in AP. It's kind of like over here in this region. It'd be like if we expanded out here. the critical point is like where the distinction between liquid and gas starts getting blurry. And so normally once we start getting into that region, they'll just cut the graph off for you. So don't stress out about that one too much, but triple point, normal melting and normal boiling are all fair questions. Okay, so some properties related to IMFs. The surface tension allows bugs or spiders in my toilet to walk on top of the water. And I'm going to zoom in, crunchy noises, to this picture of the bug right here. And what it's showing is little water, dots. And this water dot can have IMFs with all the water dots around it. When you get to the surface, this is the surface of the water, notice that it's like neat. There's like less interaction. It's like more squishy, because in the full circle, we had like a 6 spoke. But now in a half circle, we've got like 4. So if we were to complete this, it'd be like 8. So on the surface, there's like more IMFs. And that allows the bugs to like walk on the top. So surface tension, there is a greater attraction of liquid molecules to each other than the molecules in the air. Liquid at the surface behaves like it's covered with an elastic membrane. So that's a cool thing. If you have higher IMFs, then you've got higher surface tension. And viscosity is like honey. Honey is very viscous. It like, when you like try and pour honey in, it's so slow. The higher your viscosity, the stronger the IMFs are in that substance. And the last one that's the most, I'd say used, I wouldn't say most important, but the most used one on the AP exam is this idea of vapor pressure. So to get a liquid to be a gas, it has to vaporize, right? So the liquid in a container has to push itself up into the air. The pressure of the vapor pushing up into the air resulting from evaporation of a liquid, usually. When vapor pressure is equal to the outside pressure, that's when it's boiling. So if I zoom in, crunchy noises, to this picture here, I have 2 different samples of liquid, sample A and sample B. This bottom part here is the liquid phase. And every liquid has its tendency to push up into the solid phase. See how this one's kind of like not pushing very much? We can tell because it only has this much pressure on the dial, like basically 0. And this liquid is like pew, pew, like really trying to evaporate. It's got its dial cranked to almost 2. You would say liquid B has a much higher vapor pressure. It has a very high desire to evaporate. Why does it want to evaporate so bad? If it had stronger IMFs like this one, if the IMFs were doing their job and keeping the liquid together, it wouldn't want to leave so bad. And that's the deal, right? So this one must have weaker IMFs because it wouldn't be leaving the liquid state if the IMFs were holding it together better. So that's what this paper is saying here on the bottom. Because intermolecular forces are overcome when a substance vaporizes / evaporates, vapor pressure and boiling point are directly related to the strength of the IMFs. So if I just gave you this picture here and said, which of these two has the higher vapor pressure? You should be able to say this one. Look at the dial. Bam, it's at 2. It's much higher than this one over here. Or 1, 2, 3, 4, 5, 6, 7, 8 bajillion. There's so many more particles in the gas state. It is way more pressure over here. This has higher vapor pressure. And then I say, okay, that's cool. So what does that say about the IMFs? You'd say, oh, it's got weak IMFs because they aren't holding it into the liquid phase. This one's got strong IMFs. See how that works? That's what this sentence is saying. You can also use melting point instead of boiling point being liquid gas, like we just shown. You can use melting point from solid liquid, but it's not as useful. It's a lot more subtle. It's harder to see the relationship. And so generally on the AP test, they'll give you data relating to the boiling point instead, because it's easier to see the relationship there.